Alright, so thanks to the conference organisers for the opportunity to come here and present today. I'm going to be talking about using machine learning for mineral potential mapping for the porphyry copper gold mineral system in the Macquarie Arc. And as Doug just mentioned, this is some work that I completed when I was working for Kennex, but is based on a mineral potential mapping study that was done in collaboration with the Geological Survey of New South Wales in 2019. But I'd also like to thank Geoscience Australia for the opportunity to come today and for supporting my attendance through the Exploring for the Future program. So the background to this work, it started out as a collaborative project between the Geological Survey of New South Wales and Kennex in 2019, and originally involved using weights of evidence to look at mapping the potential for the porphyry copper gold mineral system in the Macquarie Arc. And basically the mineral potential map, which I presented at the Mines and Mines conference in Wagga Wagga, prior to that, which shall not be named, failed to predict the location of one of the training points used in the model, and that training point was at Kaiser. And there were also some questions around how well the model actually worked undercover. So it became a bit of a personal challenge for me, and I was trying to figure out a way to revise the models to effectively target that training point at Kaiser, as well as to see if I could improve the results undercover. So I looked at using the maps that were part of that original study. So there was no new data incorporated, there was no updated data incorporated. It was using exactly the same data as the study in 2019, but just reanalysing it using different machine learning methods. And those were using random forests and neural networks. So weights of evidence, the basis for the original study, looks at quantifying the spatial relationship between a set of known mineral deposits that represent the mineral system being targeted and the presence or absence of a particular map feature. And it's effectively looking at the relationship, the ratio between the actual number of deposits found within a certain area versus the expected number if those deposits were randomly distributed. So if a prospective area covers 10% of your study area, if you find 10% of your deposits within that 10% of the area, that's effectively a random distribution. If you're seeing more than that 10% of deposits, then you're doing better than random, and so that area might be considered predictive. So the benefits of this approach, there's a high level of user interaction to ensure that your results are statistically valid, that they make geological sense in the context of the mineral system that you're trying to target, and that they're effectively helping you to reduce your exploration search space. It explicitly handles missing data, so that if you do have some data sets with sample bias, for example, or your geological mapping is not complete, then the algorithms can handle that in the modelling process. And it is also fully reproducible. If you run the same set of input maps 10 times, you're going to get exactly the same output every time. So some of the pitfalls to this approach, there's an assumption of conditional independence. Basically, that means that the algorithm assumes that all your input maps into your mineral potential map are statistically independent of each other. And that's not always a valid assumption to make, obviously, because when we're looking at mineral systems, the different mineral systems processes do interact with each other. So we know that they're not actually really geologically independent. It is a univariate approach, so it only looks at the relationship between the training points and the input maps one at a time, and all training points are treated equally. So a Tier 1 deposit is going to be treated exactly the same as a sub-economic occurrence. The random forest approach, this is basically a decision tree algorithm which tries to predict whether a deposit is present or absent, given the presence or absence of a map feature. There's a moderate level of user interaction for the user to make sure that the results make sense, particularly after training the model using the training data. And for this particular case study, we looked at using both porphyry copper gold occurrences and barren drill holes that had not intersected mineralisation to use as negative training points. Missing data areas can be handled through imputation, which is basically putting in a mean value into areas where you don't have data. There's no assumption of conditional independence, and it is a multivariate approach. And it also allows you to weight or rank your training data so that you can rank your larger deposits higher than smaller deposits. The pitfalls to this: the random nature of the algorithm means it's not fully reproducible, but if you train your model well, your outputs, if you run it 10 times, they should look pretty similar. And the classification stage is not easily interpretable. So while it's not strictly a black box scenario, it's quite hard to interpret how you got your output from your input. Neural networks, it's basically trying to replicate a human brain, and again using training data, so your known porphyry copper gold occurrences and barren drill holes as negative training points, so non-deposit locations, and it essentially will keep learning until it gets the best result. Again, no conditional independence assumptions, and is also a multivariate approach that allows you to weight or rank your training data. Pitfalls to this: there is very limited user interaction to see whether your results make sense, and it's a kind of typical, stereotypical black box scenario. This method is also prone to overfitting, and I'll go into that a little bit more later in the presentation. Again, is not fully reproducible because there is some randomness in the weights that get assigned in the hidden layer. And especially if you have a lot of missing data in some of your input maps, it doesn't handle that particularly well. So it works much better if you have complete data for each of your input maps. So the case study implementation looked at comparing 12 different models using the weights of evidence, the random forests and the neural networks. There were 3 binary map models to compare a fair comparison of the 3 methods. 2 164 binary map models, which were testing using the statistically valid maps generated using the weights of evidence. 2 197 multi-class map models, which was looking at how the models worked when there was no favourability criteria applied, so no specific buffer thresholds or anything, just let the computer try and figure out what the most effective thresholds should be, and 5 different geophysical models, so only using geophysical input maps to see how effective the different methods were for targeting undercover. And this is basically a table here showing how the different input maps and training points used in each of the models. The interesting thing to note here is that these input maps, the multi-class input maps, literally every pixel within the Macquarie Arc study area has its own unique condition, so that no 2 pixels in the Macquarie Arc share exactly the same set of geological characteristics of each other. So all of the maps and the training data were generated using ArcGIS, and the weights of evidence also run in ArcGIS, but the random forests and the neural networks were implemented using R, because basically it was a lot faster. Comparing the results, I looked at 3 different assessment criteria. So firstly, the reduction in the exploration search space from the output mineral potential map. how well did each of the models predict a separate subset of validation porphyry copper gold occurrences, and how well did each of the models work undercover. And so you can see in this table here the amount of prospective area in each of the models. So this is with the models being binary, so the output maps were prospective and unprospective area only. How well the models were trained. So for the random forest models, the training accuracy was determined from the confusion matrix, so higher values are better. And for the neural networks, the training accuracy is based on the loss function and lower values are better. So we can see here there's quite a bit of variation in the training accuracy for the different models, and essentially found that there are a number of issues here relating to the amount of prospective area coming up in some of the models, about 50% for some of them, more than 2/3 for other model, and also some issues with the validation occurrences. So about 6 of the models have some issues with various aspects of the outputs and with the training. Looking at the prospective area versus the validation point prediction, a model's no better than random if it requires 80% of the study area to capture 80% of the known deposits or the training points or the validation occurrences. So what we're really looking for is a small amount of area but a high capture efficiency of the training points and the validation occurrences. So the statistics basically show that the 164 binary map random forest model was the most effective, but a couple of others were also pretty good. The weakest results typically ended up happening when the multi-class maps with no favourability criteria were applied that were used as input, regardless of whether that was using all data sources or just the geophysical input maps. So the ones that didn't have the favourability criteria applied tended to have weaker training results and also poorer outputs in terms of the prospective area and the validation. So out of the 12 models that will run, realistically we can probably ignore 6 of them because they have issues with various aspects of the modelling process. And this basically comes down to what is known as overfitting of the model. And this is a more common occurrence with neural networks and is essentially the result of having too many unique conditions or feature vectors that need to be predicted and not having enough training data. And so this impacts the use of imputation methods when dealing with missing data. And there are methods that have been developed to try and overcome this lack of training data because mineral occurrences are rare events and we're probably never going to have enough to run particularly complex big data type models for mineral potential mapping. So these kind of methods that exist to simulate an increase in the number of deposits or in the deposit class in the training data set. And they tend to make some assumptions about the nature of the input maps and the mineral system that are being modelled. So the porphyry copper gold case study here is a really good example of where these assumptions are violated. And so I'm just going to run through a really brief cartoony type example showing what the issue is. So we have here a hypothetical mineral system where we have a known deposit at location 1 located within an intrusion. And we use a data augmentation method to create an artificial deposit training point at location 2. So we see here the unique condition for training point 1 and the unique condition or the feature vector for training point 2. So having our augmented training point 100 metres away from the intrusion may make geological sense for this particular mineral system where it's the proximity to the intrusion which is important. If we then move to a mineral system where it's the host rock which is important and it's not buffered, we have our training point at location 1. If we then put an augmented training point, deposit training point at location 2, what we find is when we look at the unique conditions, the I-type intrusion is not geologically similar to a sandstone, so it's put the augmented training point into a geologically non-permissive setting. Right? And this becomes more of an issue when we start integrating our non-deposit training points, because if we put if we have a barren drill hole, for example, at location 3 to represent a non-deposit location, and that's 300 metres away from our intrusion, that may make geological sense. But if we come back to this host rock example, what we now have is a situation where the unique condition at the augmented point at location 2 is identical to the unique condition for location 3. And the model doesn't now know how to classify this sandstone unit. Should it be prospective or unprospective? And it becomes more of an issue as you start adding more of these augmented deposit points and they start to conflict with the non-deposit locations. So although I did attempt to use this particular method called SMOTE to try and increase the size of the deposit class to overcome this problem with overfitting, unfortunately it didn't actually work, because I got really high error rates because of this conflicting issue between the augmented deposit locations and the non-deposit locations that were pulled out of the barren drill holes. And this is an example output. It's although the colour scheme on this does go from 0 to 1, it looks like the area is only 1, or the minimum value I think is 0.125. And it doesn't look like there's any intermediate values because it's overfitting to the training data. There are actually a few pixels in here in that intermediate scale, but you can see quite visually that it is heavily overfitting to the training data. So the next aspect, I guess, of the modelling was to see how effectively they worked undercover. And so the original set of models were run using multiple data sources. So for example, the seamless geology, the fault attribution data set, surface and downhole geochemistry, geophysics, remote sensing, but when we looked at the outputs from those models, they didn't appear to be particularly effective at targeting undercover. So basically designed separate models using only geophysical input maps, so different mag gravity filters, worms, etc., which helps to reduce the interpretation bias, and also being geophysics, they help us to target undercover. And there's also a good level of consistency in the map detail, assuming the geophysics has been appropriately levelled, and this is one of the benefits of using government geoscience data. They're very good at doing this. So the geophysics-only models appear to be more effective at targeting undercover, which is good. And I'll go through the different outputs from the different models. So the geophysics-only models had a much lower training accuracy than the models using a variety of the data sources. I'm not 100% certain of the specific reason for this, but there's a few ideas around it relating to whether the regional scale geophysics that was used in this modelling accurately discriminates the geophysical signatures of the different porphyry copper gold occurrences used as the training data in the modelling. So as we've seen over the last sort of day and a half, I guess, the geophysical signatures of some of these deposits can be quite different due to the different deposit geometries. It's like comparing Cadia and North Parkes. You're seeing quite a different geophysical response in the regional scale data. Also, whether the non-deposit training points have two similar geophysical characteristics to those deposit porphyry copper gold training points. It's also worth noting that the lack of interpreted data sets in the models does mean there's probably some false positives in them that have nothing to do with the mineral system being targeted. So they could represent sources that significantly post-date mineralisation. And this image down the bottom here is an example of why the radiometrics didn't get put into these geophysical models. This is a mine site right here, and you can see it showing up in the radiometrics. So this is not really anything geological, it's the buildings at the mine site which are showing up. So looking at the outputs, what I've got here is the binary classified mineral potential maps. So the blue is unprospective and the red is prospective. And I've put a mask over the top of them, which is essentially the depth to basement map from the New South Wales Geological Survey. So the darker colours are essentially the outcropping areas, the lighter grey colours is less than 100 metres cover, and the more transparent colours are the greater than 100 metres cover. And you can see here in the transparent colour that most of it's blue, so there's not much prospective area for these maps that have been designed from the multiple data sources for the weights of evidence, the random forests and the neural networks. Looking at using the 164 binary maps from the data source, from the multiple data sources, again, you can see there is very little prospective area in those undercover areas. But when we start to look at the 197 multi-class maps that don't have the favourability criteria applied, we can start to see some of those, some prospective area coming up in these interpreted undercover areas. However, as I was showing in those earlier tables, there are some issues with some of these models. So the random forest model has too much prospective area. About 50% of the Macquarie Arc was coming up as being prospective. And for the neural network model, it had really poor training results and again too much prospective area for it to be useful. Looking at the geophysical only maps, so the maps that only included the different geophysical filters from the mag, the gravity, the worms. Again, we can start to see some prospective area coming up undercover. But if we eliminate the models where we have some issues, we're left with the random forest model, which if I zoom into the area where we have our porphyry copper gold deposits used to train the model, what we can see is that there is some prospective area coming up in this quite well explored part of the Macquarie Arc. And so there's some interesting areas that are coming up here. This is just to the northeast of Cowell, and if I plot up on just over here, the green dots are the location of the drill collars from MinView, and the smaller white dots are the location of all the metallic mineral occurrences. So we can see there's actually some red area or some prospective area interpreted to be undercover within the Macquarie Arc, where there appears to be very little exploration history. I'm not sure of the reason for that. But that's come up as it is. So, and then just looking at the geophysical only input maps where there are no favourability criteria applied, again, you can start to see some prospective area in these undercover areas. But again, there's some issues with these models for various reasons, being poor training results or poor validation results. So just summarising all of this, all of the random forest and the neural network models found Kaiser. So that was what initially kicked off doing this machine learning work, but There's some issues with some of the other training points in a couple of the models. So one of the neural networks models failed to find North Parkes and NASDAQ. This is the porphyry copper gold sort of mineral system more generally. So there are some epithermal deposits in the training data set to look at the different end members for the porphyry system. And one of the other neural networks models failed to predict 2/3 of the porphyry copper gold training points, so it was effectively a useless model. So out of the 12 models that were run, 6 should probably be ignored because they failed to produce a reliable or a robust result due to having poor training statistics, poor classification results in terms of being able to predict the validation occurrences, or some kind of violation of assumptions. The results essentially indicate that using the pre-classified maps that have got favourability criteria applied to them produce a more robust result regardless of which method was used. The models run only using the geophysical inputs, do highlight prospective area under cover, but just the sort of cautionary note, I guess, careful scrutiny is required. I wouldn't just go drill them. They should be cross-validated with other data sets where possible to reduce the chance of chasing false positives. The most consistent model across the board seemed to be the 164 binary map random forest model, but the geophysics only model using the binary input maps for random forest was also pretty good. So where to next with this? Now that I'm at GA, we're hopefully looking to expand on these ideas relating to targeting undercover as part of national scale mineral potential mapping work that's being done under the Exploring for the Future program. Look at potentially re-evaluating the results through the data that's been compiled into the EGGS database, which will include a depth to Paleozoic grid for the East Lachlan at some point, and sort of a more big sky sort of question. Given how well explored the Macquarie Arc is, why are there multiple mineral potential maps that are showing essentially buried porphyry targets pretty close to known mineralisation that have no evidence of exploration drilling? Is it an issue with depth of basement? Is it an issue with land access? Is there some kind of critical factor that the geophysical-only mineral potential maps aren't recognising, or is it an exploration opportunity? I don't know. That's a question to sort of look at more in the future. And I will leave it there. Thank you.